Hi everyone. Today we're going to be beginning our notes on transformations of functions. Today we're going to be discussing input and output. Let's start with the warm-up. We're giving a verbal description of a function. Write the algebraic representation of that function. So for 1a, to evaluate f of x, divide the input by 3 and add 4 to the result. So if I want to evaluate f of x, I'm going to take my input x and I'm going to divide it by 3. And from that resultant quantity, I'm going to add 4. So our answer, f of x is equal to x over 3 plus 4. 1b, to evaluate g of x, subtract 4 from the input and multiply the result by 6. So again, to evaluate, we're going to subtract 4 from the input, so x minus 4, but then we want to multiply that entire quantity, that result, by 6. So I'm going to group this in parentheses and then multiply by 6 to show that I'm multiplying that result by 6. Okay. Number 2, use the function y equals 2x minus 4 to answer the following questions. 2a, if you're evaluating the function for x equals 3, describe the steps that you would take. So notice here that we are evaluating the function. Whenever we're evaluating a function, we're going to use our order of operations, or PEMDAS. And we're going to go in that order. Now, as a reminder, PEMDAS is parentheses, exponents, multiplication and division, and addition and subtraction. So in order to evaluate this function, our first step would be to multiply 3 by 2. Right? When we plug in 3 in for x, we're going to first multiply it by 2, and then our second step is to subtract 4 from the result. Okay? For 2b, now we're saying if we're solving the function for x, then which steps would we take? So just like when we're evaluating, we use PEMDAS. When we're solving, we're going to do reverse PEMDAS. So we're going to start and deal with any addition or subtraction first, then multiplication and division, then any exponents, and then any parentheses. So we're going to go in the reverse order. So if I wanted to solve for x, the first thing that I would have to do is add 4 to both sides of the equation. After we do that, then we have to divide both sides of the equation by 2. Okay? So I just wanted to do a quick summary of evaluating a function and getting the function outputs, or solving for the input of the function. This order of operations, when evaluating, we're always going to do in PEMDAS order, and then in solving, we're always going to do in reverse PEMDAS. Okay? So in this unit, we're going to explore 4 different types of transformations. We're going to explore horizontal and vertical shifts, reflections over the x and y axes, vertical stretches and compressions, and horizontal stretches and compressions. All right, let's go ahead and flip the page and begin talking about horizontal and vertical shifts. So below here, I have a table of values for h of x and a graph for b of x. First, we need to identify which operations need to be applied to the input or the output, and then we'll fill in the table for h of x minus 3, and then graph for b of x plus 3. Finally, describe the transformation that's occurring in each example. So let's start with the table, h of x. So I'm looking at this table, and to evaluate h of x minus 3, we're simply subtracting 3 from the output. Now, just as a reminder, remember x is our inputs, and then h of x is our outputs. So if we're subtracting 3 from the outputs, we can simply just take our h of x values and just subtract 3 from them. So h of x, so h of 2 is 3. We're going to subtract 3 from that, and we get 0. H of 3 is 4. Subtracted 3 is 1. H of 6 is 5. Minus 3 is 2. And h of 11 is 6. Minus 3 is 3. Okay. Graphically, we would see this as a vertical shift down 3 units. Okay, because we're taking all of our function outputs and we're subtracting 3. Every output decreases by 3. Okay, now let's look at the graph of b of x. So here, we're looking at b of x plus 3. So here we are adding 3 to the input. Now we need a couple values here, so I'm actually going to construct a table of values, x b of x, and I notice 4 key points on here. I see one at the end here. We've got a minimum, a maximum, and then that other endpoint. The coordinates for that first endpoint are -4, 1. That next point has coordinates -1, -2, and we have 2, 3, and then 3, 1. Now, in order to find the transform function, let's make another table of values, x b of x plus 3. We only have these 4 original values of the function. So when we're adding 3 to the input, we have to ask ourselves, for what x value, when we add 3, is going to give us -4? Like we could set up the equations, x plus 3 is equal to -4, for example. So for what number plus 3 is going to give us -4? The answer is -7. And when we evaluate -7, if you were to plug in -7 in for x inside the function b of x plus 3, it would evaluate to 1, that same output. Okay? The next one, again, for what value of x, when we add 3, do we get -1? The answer is -4, and this evaluates to -2. For what value of x, when we add 3, do we get 2? The answer is -1, and then when we evaluate, we get 3. And finally, our last point, we have 0, 1. Okay, so if we were to graph this, I'm going to remove my red dots here just so I can see the transform graph easily. If we were to graph this, go ahead and plot your points and then connect all of your points, and we'll see what the function looks like. So -7, -1 is right here, -4, -2, -1, 3, and 0, 1. So graphically, let's see if we can come up with a description of what's going on here. We have our original function here in black and our transform function here in red. The description of this transformation is a horizontal shift to the left 3 units. All of our function inputs are shifted to the left 3 units on the graph. Okay, now let's talk reflections. So here we have the table y equals f of x, and we have some values here. We're going to fill in the values for -f of x and f of -x. Okay, so for y equals -f of x, we are going to plug in the same inputs for x. Notice that that negative out in front does not affect the input of the function, but rather the output. So all of those same inputs are totally fine to plug in. But then notice for our function outputs, it's just going to take the sign and it's going to flip it. That negative out in front is going to flip the sign of any of our outputs. So instead of 5, we get -5. 0 stays 0. Instead of -3, we get +3. We get +4, and then +3. Okay. For the next table, y equals f of -x, all of our function inputs are going to flip signs. So instead of -2, 5 in the original function, we have +2, 5. Instead of -1, 0, we have +1, 0. 0, -3, that stays the same. +1, -4 becomes -1, -4. And then 2, -3 becomes -2, -3. Okay, let's go ahead and graph each of these. So we'll start with the parent function, y equals f of x. Or I should say the original function. So y equals f of x. We have -2, +5. These are 5 by 5 grids, so it's all the way at the top. -1, 0. Our y-intercept, 0, -3. 1, -4. And 2, -3. So we've got part of what looks to be like maybe a quadratic. Okay. Now, when I graph y equals -f of x, let's go ahead and plot those points. We have -2, -5, so that's at the bottom of our grid. -1, 0, 0, 3, our y-intercept, 1, 4, and 2, 3. Connect those dots. And you might be thinking what observations you're making here. We'll go ahead and describe that below. But let's go ahead and graph that last one, y equals f of -x. So we have 2, 5, all the way at the top of the grid. 1, 0, 0, -3, -1, 4, -4, and -2, -3. So remember, this section talks about reflections. So when we reflect, or when we put a negative out in front of the function or affect the function output, that's going to be a reflection over the x-axis. When we put a negative in the input of the function, f of negative x, that's going to be a reflection over the y-axis. So the relationship between f of x and negative f of x is that negative f of x is f of x reflected over the x-axis. Okay, let's go ahead and flip the page. Now let's talk about multiplying by a scalar. These are our stretches and compressions. We're going to talk about both vertical and horizontal stretches and compressions. So we'll start with the original function, y equals f of x, a different function now. We have the table of values here. For the next table, we have 2f of x. So we're taking all of our function outputs and we're doubling them. So -2, 0 stays -2, 0. -1, 2 becomes -1, 4. We're doubling that function output. 0, 0. We get 1, -4, and then 2, 0. Now for y equals f of 2x, remember, we have to ask ourselves, we need to get these 5 values here. We need to ask ourselves what number times 2 gives us -2. The answer is -1. What number times 2 gives us -1? The answer, -1/2. What number times 2 is 0? Well, that's 0. What number times 2 is 1? 1/2. And then what number times 2 is 1. All of our function outputs stay the same, so we still have 0, 2, 0, -2, and 0, respectively, moving down the table. Okay, let's go ahead and graph this and see if we can come up with a relationship between the scalar and its transformation. So here we have f of x. We have -2, 0. We have -1, 2, 0, 0, 1, -2, and 2, 0. So we're going to see more of this later, but this looks to be like a sine or a cosine graph, part of one anyway. And then for y equals 2f of x, let's go ahead and plot those points. -2, 0, -1, 4, 0, 0, 1, -4, and then 2, 0. So you might already be noticing what's going on here. When we multiply by a scalar, we get like this taller graph here. And then finally, we have for our last graph, -1, 0, -1/2, 2, 0, 0, 1/2, -2, and 1, 0. Go ahead and connect those dots. Okay. So when multiplying by a scalar, when we multiply the function output by a number greater than 1, then we're looking at a vertical stretch by a factor of that coefficient. And then when we multiply the input by a number greater than 1, we're looking at a horizontal compression by the factor of its reciprocal. Okay, so then the relationship between f of x and 2f of x is that 2f of x is f of x stretched vertically by a factor of 2. Okay. All right. Let's now multiply by numbers less than 1. So again, we have that same f of x, that original function. So we have -2, 0. We have -1, 2. I'm just going ahead and graphing this right now, just so that we can remind ourselves what this function is. 1, -2, and then 2, 0. Okay. Now, when we multiply our function outputs by 1/2, we take all of these values and we divide them by 2. So now we have -2, 0. We have -1, +1, 0, 0, 1, -1, and then 2, 0. So graphing this, we have 2, 0, -1, 1, 0, 0, 1, -1, and 2, 0. Okay. And finally, y equals f of 1/2 x. Again, we have to ask ourselves what number input, what should our x input be? So what number times 1/2 gives us -2? The answer is -4. What number, or what half of what number gives us -1? The answer -2. We have 0, 2, and 4. Our function outputs are unaffected, so we still have 0, 2, 0, -2, and 0. So let's go ahead and graph this. We have -4, 0, -2, 2, 0, 0, 2, -2, and then 4, 0. Okay. So again, you might notice that this scalar multiple, right? If we multiply the output of the function by a number less than 1, then we get a vertical compression by a factor of that coefficient. And then if we multiply the input by a scalar less than 1, then we have a horizontal stretch by that factor, the factor of its reciprocal, I should say. Okay, so the relationship between f of x and 1/2 f of x is that 1/2 f of x is f of x compressed vertically by a factor of 1/2. Okay. All right, we're almost done here. Last page. Now let's consider if I have the ordered pair 3, 5 is on the graph y equals g of x, then we have to determine what inputs and outputs would we get from the transform functions given below. Okay, so here we have y equals -g of 2x minus 3. So we have to describe the transformations. So for the input, the first transformation is that we are going to have a horizontal compression by a factor of 1/2. The actual x input would be if we were to take that input 2x and we want to set it equal to that number that we were given. So here we have the input is 3. So we're saying what number doubled would give us that input? The answer is 3/2. For our function output, the first thing that we have to do, remember order of operations is important. When evaluating the function output, we're going to first multiply by -1, and then we're going to subtract 3. Well, we just learned that multiplying by -1 is a reflection over the x-axis, and then subtracting 3 at the end is a vertical shift down 3 units. Okay, so if our original function output at x equals 3 is 5, when we evaluate y, we get y is equal to negative, and then our function output, 5, and then minus 3. So order of operations, again, we have -5 minus 3, which is equal to -8. So we know that on the transform function, the point 3/2 -8 exists on the transform function. Okay, number 2. So here, what affects the input? We're looking at this part right here. I always like to factor these. I always like to get x by itself. So this is equal to the quantity negative times the quantity x minus 5. Okay, so you can always write that function input like that. And so when I read this, I would do order of operations here and say that there is a horizontal shift right 5 units. And then we would have a reflection over the y-axis. Now, if you didn't factor out, then you would first have that reflection over the y-axis, and then you would shift left 5 units. Okay. So when evaluating, we're going to set that input. I'm going to take the original one, negative x plus 5, and then set it equal to 3, and then solve for x. So we subtract 5 from both sides. We get negative x is equal to negative 2. And then dividing both sides by negative 1, we get x is equal to 2. Now the function outputs, all we have is that scalar multiple in the front of 1/3. So this is a vertical compression by a factor of 1/3. So then we would have y is equal to 1/3 times that function output, which we know is 5. So y is equal to 5/3. Okay. Last problem here. Here we have y equals g times g of 3 times the quantity x minus 1, and that's all minus 6. So here, our function inputs, the very first thing that we do is a horizontal shift, right 1 unit, and then we have a horizontal compression by a factor of 1/3. Okay, so to find that function input, we're going to take 3 times the quantity x minus 1, and we're going to set it equal to 3. To solve for x, we divide both sides by 3. We get x minus 1 is equal to 1, and then adding 1 to both sides, we get x is equal to 2. Finally, our function outputs, we only have one transformation to the output, and that's this minus 6 at the end. This is a vertical shift down 6 units. Okay. All right, so to evaluate, we have y is equal to our function output, 5, and then minus 6. So we have y is equal to negative 1. All right, so these have been our transformation rules. We're going to get so much practice on this, so we'll see you tomorrow. Have a great day, everybody. Goodbye.